Alrighty, so today we will have our exam review. Our first exam, exam one, is going to be Thursday. And just to explain for those who did not have me last semester or in a previous semester, how the tests work, at least as they are done online. Basically, the best way to describe it is exactly how the homeworks are done. The test will be posted onto Canvas in the module section. There's going to be a new module for exams. And in that module, you'll have exam one posted. It'll be Thursday morning. Basically, you download the PDF. It's the test. You work that out. You could either, print out the PDF and work it out on the test itself, or if you wanted instead to just do it on blank sheets of paper separately, that's fine too. You work everything out. Of course, you have to show all your work, because if you don't, number one, the natural assumption of a professor is if someone doesn't show me how they got their answer, they just show an answer sitting there, then I'm going to assume you got the answer from someone else. So show your work. And the other benefit, obviously, is I give partial credit. So let's say you worked the problem out correctly, but you typed something into the calculator wrong or something like that, or you forgot to convert a unit or something. Then rather than just marking everything wrong, I can look at your work, see where you went wrong, and give you partial credit. So you show all the work, and then of course, your answer, I ask that you box your answer just so it's easier for me to be able to look through what's going on and see where your answer is. Most people, it's not a big deal, but sometimes people are kind of interesting in how they work out problems, and the work is all over the place, little pieces here, little pieces there, and it's really difficult to see what's what. So box your answer. Also, I've gotten a lot of times students are unsure how to work a problem, and so they'll work it out two different ways to get two different answers. And like giving me, hey, you choose which answer you like. Well, no, it doesn't work that way. You're going to give me one answer and box that answer. So anyway, you work out the problem, show all your work, box your answers, and then whenever you're done with the test, you upload it back to Canvas, you submit it back just like your homework submitted, and that's that. The deadline will be 11:59 p.m. that night. Okay, so you have the full day to work on it. Obviously, because it's a test day, we won't be having class. So if you wanted to, you could take the time where we would normally be having class to go ahead and work on the test. Or if you want to wait till later in the day when you get home, or whatever the case may be, you have the whole day to work on it. Not only is that just so that we avoid, time issues, or my internet went out at this time, or anything like that. Also, if there is some technical difficulty, so say you did the test and you tried submitted it, but something's going weird with Canvas and you can't submit it, well, you still have some time to contact me, let me know what's going on, and we could figure out something, rather than I get an email the next day and say, hey, I couldn't submit my test yesterday, can you accept it now? Well, how am I supposed to know if you actually had technical difficulties, or did you just want more time to take your test? Did you forget about the things like that? We avoid all those situations. I give you the full day to work on it. You work on it at your leisure, but obviously, try to submit it early. That way, if something does come up, you have time to email me, let me know, and then we'll work that out between us. So that's kind of the formality. Of course, the formula sheet for the class is posted on Canvas, so all the formulas you may need are there. But since this is online, And I'm not going to be sitting there watching you take your test. You have all the resources at your disposal, and if you've been taking notes, the practice problems posted on Canvas, the homework problems, my videos, whatever the case is, you can watch them, you can look at them as you're doing the test. I have no way to ensure that you don't use outside resources, so I'm not even gonna pretend like I'm going to. The only thing I do say, my only one true rule is you do not basically talk or discuss the test with other people, to other students. Okay, you take the test yourself. I don't want people copying answers from each other, working together in a group or anything like that, because I've been teaching for a number of years. Number one, it's really easy to see when people are copying answers, especially with a topic or subject like physics, where you actually have to do the math and mistakes can be made at any step. Well, I see all the time someone worked out the problem incorrectly, got a bad answer, and then all of a sudden there's 7 other people with that same bad answer. What are the chances all 8 people made the same weird mathematical mistake at the same spot and got the same wrong answer? You know, I'm not stupid. So I just ask, take the test yourself. You have all the resources at your disposal. There's no reason you can't do it yourself, and see how you do. So don't copy off of others. Don't work in groups. That kind of stuff you could do for homework and practicing problems, but not for the test. All right, so that's kind of the formality of the test. How many questions, things like that. I'm going to make the test, even though it's an online test, a take-home test, basically. It'll be the same length as a regular in-class test would be. So normally this would be an hour and 15-minute class. And I found that generally speaking, 5 to 7 questions is kind of a good length for these types of tests. So that's what you can expect. The test will have between 5 and 7 questions, depending, if some of the questions can be faster, some are longer. And so I modify it a little bit, but between 5 and 7 questions is what you can expect. All the questions are weighted equally. So let's say they're all worth 10 points. So it's not like one question is worth more than another question, because that's the harder question. And so because of that, just as a strategic thought, work those problems you know how to do for sure first, get those right, and then the ones you're unsure about, save those for last. That way, at the very end, if you run out of time or something like that to submit the test, at least those questions you could answer for sure, you're going to get the points for. And don't waste, valuable resources on a question you don't know how to do, which is equally weighted with a question you do know how to do. Don't screw yourself out of a good question because you're working on the bad question first. So that's that. Now, the topic. Oh, before I get to the topics, are there any particular questions on the formality or the format of the test itself? Okay, I will also say along with it, obviously you need a calculator. I don't want to see you have the equation sitting there, you plug the numbers in the equation and you just leave it like that. You have to get answers. So make sure you have a calculator. And make sure you know how to use a calculator appropriately, of course. Yeah, so the topics, what topics will be on this test? Well, generally speaking, what I do for all my tests is all the topics we've discussed since the last test are going to be on this test. And since this is our first test, that means all the topics we've discussed since the beginning of the semester. Now, there's a caveat there in that I will not be testing you specifically on math review stuff. So if you remember at the beginning of the semester, we took the first couple of weeks and just worked on the math. We did algebra review, trigonometry review, vector review, things like this. Well, there's not going to be any questions on this test that are purely trigonometry or something. Instead, any of that math that you need to know will be tested through the actual physics questions themselves. So the first real topic, which will be on this test, starts, of course, with thermodynamics. And that is calorimetry. So if you remember calorimetry, this topic dealt with things like you have a container. In this container, you put these different materials. Each material starts at its own certain temperature. You mix them all around, you let them sit there for a while, and eventually they come into equilibrium. They all reach some final temperature together. And you want to know what the final temperature will be. Or you have some hot coffee in a cup and you want to put some cold milk to make the final temperature 70 degrees. How much milk should you add? Those styles of questions. And so what we saw was we had two real big equations, Q equals Cm delta T. Okay, and this was used when you have an object in your system, which is going to change temperature. So how much heat is added or taken away in order to change the temperature by this amount? The other was Q equals M times L. And this dealt with those parts of the system where you could change the phase. So if you put ice in some hot water, the ice can melt. So there must be a factor in your equation which deals with the melting of the ice itself. And you combine these together to do your actual equation, which would be something like Q1 plus Q2 plus Q3, however many things are in your system is equal to 0. So if it's a question like you have some hot coffee in a metal cup and you put some ice in the cup and you want to know what's the final temperature going to be, well, there's going to be Q for the coffee, plus Q for the cup, plus Q for the ice, plus Q to melt the ice, and then another Q because now that the ice is melted, that melted ice can heat up. And you'd add all those things together. Each one is either Cm delta T or M times L. Add them all up, set it equal to 0, plug all your numbers in, and there's going to be something in the equation, which is the unknown variable. And then you just do the algebra to calculate that unknown variable. Things to watch out for in this topic, of course, and making sure you convert your units. A lot of times I've seen, as I graded the homework, the mass may be given as 150 grams of ice, but then I see someone, lots of students actually, in their calculations, don't convert it from 150 grams to 0.15 kilograms. They leave it as 150. Well, you can't do that. In order for these equations to work, you have to use the correct units for everything. And for mass, the correct unit is kilograms. Temperature generally in physics is Kelvin. However, because delta T is in this equation, the trick for delta T is that a delta T of Celsius is the same as Kelvin. So we can get away with using Celsius here if we want to, or you could use Kelvin. And, truly speaking, you're supposed to be using Kelvin. So that's calorimetry, first big topic. Then we discuss conduction. And with heat conduction, you had things of the sort where you have a multi-layered system, so maybe some wall and some insulation, and you have the inside of your house versus the outside of your house at two different temperatures. And you want to know how much heat will be sent, or what's the heat transfer rate through this wall system by conduction. And we know that the equation for such a thing goes like the heat transfer rate, Q over T, the amount of energy which goes through by conduction per second, is given by K, conductivity, that depends on the material, times A, how big is this system, the area of the system, delta T, which is the difference in temperatures between one side of the layer and the other side of the layer, all divided by L, which is the thickness. How thick is the wall? How thick is this layer? And from here, you can answer questions, what's the heat transfer rate? Or if I wait 3 hours, how much energy will pass through? All sorts of things like that. But then we also saw that if we have a multi-layered system, so instead of just one layer, but we had 2 layers, then what we would have to do is we'd use the fact that the heat transfer rate, Q over T, for the first layer must be equal to Q over T for the second layer. And so we would use this fact, plugging in Ka delta T over L for the first layer and the same for the second layer. We would be able to answer another question like, given you have a multi-layered system, what's the temperature in between the layers? You know the temperature on one side, the inside of your house, the temperature on the outside of your house, but what about the temperature between the wall and the insulation? You could calculate that using this. And then once you know it, you could say for the whole system, as the heat is transferred through the system, it has to go through the first layer and it has to go through the second layer. Thus, if I want to know the heat transfer rate through the whole system, I can choose either the first layer or the second layer. What's the heat transfer rate through that layer? Whatever that number is, that's the heat transfer rate through the system as a whole. Okay. And that was conduction. Again, I may be looking for heat transfer rate, or I could be looking for the amount of energy in a certain amount of time, or how long should I wait so I get this much energy, all that sort of stuff. And then lastly, the final topic, which we just finished up, is radiation. Heat transfer through radiation. And these types of questions were of the form, you have a star of a certain radius and it's at 10,000 Kelvin. And you want to know what's the power radiated by the star. Or you have a metal cube and you know the size of this cube and it's at 600 degrees Celsius. How much energy will it radiate per second? Or if I wait 1 day, how much energy will it radiate? Things like that. The equation, Q over T, the power radiated, or the heat transfer rate, the same thing, is given by sigma, which is called the Stefan-Boltzmann constant. Epsilon, the emissivity. This particular material radiates at 30% or is a perfect radiator, all that kind of stuff. A, the surface area of the material. Obviously, a bigger thing can radiate more energy than a smaller thing for the same temperature. Times the temperature of the object to the 4th power. And with this, we see, we now have an equation sitting here, which requires the temperature and not the change in temperature or the difference in temperature. And because of that, we need to make sure that the units we're using here are Kelvin for the temperature. So if you have Celsius, you have to convert it. And also in the area, you have to make sure that the objects, when you're calculating the area, it's in meters, not centimeters, not millimeters, nothing like that, but meters. So make sure all the units are converted, and then you could use this equation. Further, we saw that it's possible to generalize this to a situation where we put this object in a background environment, which is at some second temperature. And so we modify the equation to allow for that by just changing this a little bit. Now, instead of just t to the fourth, you now have the object at one temperature, and it's placed in an environment which is at another temperature. So it's t object to the fourth power minus t environment to the fourth power. And again, Kelvin is units you need to use for temperature here. You cannot use Celsius for any of this in radiation. But these are basically the same equation. The second equation is the main one. That's the general equation. The first equation is the second one under the assumption the temperature of the environment is just 0. And so if you're given a problem and I don't tell you anything about the environment's temperature, then you just assume it's 0, and so you're using the first equation. But of course, if the problem tells you, hey, you put this metal cube into a refrigerator that's at this temperature, well, now you have information about the environment's temperature, so you better use it. And that's it. Those are the topics. So basically 3 topics. They're all thermodynamics. We have calorimetry, which was its own set of types of problems, all about coming up with the final temperature or equilibrium temperature or stuff like that. Heat conduction, you have layers, and heat wants to pass through these layers. So you're looking for the heat transfer rate or how much energy will pass through per second or things like that. And then you have radiation. An object's at a certain temperature and it'll radiate energy. What's the power radiated? How much energy will you get out of it after waiting 1 year or anything like that? All right, so those are the topics. As I said, 5 to 7 questions. So let's just, I don't have it done. I haven't made the test, so this isn't exactly true, but assume something like 2 questions per topic. A little bit of everything. Each one, like I said, equally weighted. They're all 10 points each. And at the end of the day, I created the homework questions. I made them up in my head. I created the practice problems that are posted on Canvas. And I create this test. I don't look it up. I don't have a test bank like a lot of professors get or anything like that. I just make these questions up. And so if you want to get an idea of what the questions on the test will look like, well, just look at the practice problems that are posted on Canvas. I made those questions up. That's how my mind works. And so obviously my test questions are going to have that same type of form. Now, they may not be identical. In all likelihood, they'll have different numbers. But the way the question, the type of questions, the way they're worded, the way they look, just work the practice problems that are posted on Canvas and the homework problems that you've been turning in. If you work those problems, I promise you, there will not be a question on the test that is unlike that stuff. And so in my estimation, if you practice those problems, there's no reason you shouldn't make 100 other than, little simple math mistakes you might make along the way. You'll know how to work all these problems. You will have seen similar things and we'll be able to work them out. So that's my recommendation. As you study for this, go on to the Canvas, download the practice problems and the solutions and work them out yourself. If you're having trouble with them, look at the solutions. See how I work the problem out. Once you see how I do it, you try to do it yourself, but don't just look at the solutions and say, oh yeah, I follow along. This all makes a lot of sense. Because unfortunately, the way our brains work is if we see someone doing it and it makes logical sense, then it's perfectly fine. And we think we understand it completely. But when we have a blank sheet of paper, all of a sudden, our mind can't follow what it should have been doing if we're not very, very comfortable with the material. And that's where we see where we're lacking information. We don't really know what's going on. So practice the problems, see if you could get them. If you could work all the practice problems out and get them right, then this test is going to be a breeze. If you're having trouble with particular questions on the practice problems, then that's the area you should focus on. Look in the previous lectures we've been doing and work those examples. Look at the homework problems, work those problems again. But there's no reason that you should find anything on this test unusual or different than anything we've been doing thus far. All right, so that's my spiel on the test, and that's really all I have. Do you have any questions about any of this, any of these topics, or the test itself, what to expect, anything like that? All right, well, if you have no questions, I'm done, so you're free to go. I will email you when the test is posted on Thursday, but like I said, it's going to be Thursday morning, but I'll remind you when it's up. So definitely look out for it. Also, don't forget, you do have a homework problem due tonight, a problem on radiation. So be sure you're working on that. If you have not already submitted it, be sure to submit it. You don't want to miss a homework problem. And other than that, I wish you luck in studying for the material, and feel free to email me if you do have any issues as you're studying and you're unsure of something. I'll be happy to help. So I'll see you on.
I have a question.
Yeah, what's up?
Basketball, we leave on Thursday morning. So could you like post the test at like 6 a.m. so I could get it printed out before we leave?
Yeah, that's no problem. In fact, go ahead and email me. If you can remember Wednesday evening to remind me. That way, if something happens, I can always just send you a copy of it, so you'll have it in your email as well.
Okay, thank you.
Yeah, I'll be sure to try to have it posted as early as possible. Any other questions? All righty. Well, I guess I will see y'all later.